Welcome to the General Chemistry 2 class. This section is on chemical equilibrium. This lesson is about equilibrium constant. Let's begin. In this lesson, we will write expressions for the reaction quotients or equilibrium constants. In 1864, K2 Gilbert and Peter Wage introduced the law of mass action, which states that a reversible reaction at equilibrium has a constant ratio of the concentrations of products to the concentrations of reactants at a given temperature. Mathematically, for the following reaction, the corresponding constant, called the equilibrium constant, K, is given by the following equation. The letter enclosed in square brackets denotes the concentration of a substance in moles per liter at equilibrium. The superscript is the corresponding stoichiometric coefficient of the substance from the balanced chemical equation. The equilibrium constant can be used to determine whether the forward or the backward reaction is more favored. More details will be discussed in another lesson. A homogeneous equilibrium involves a mixture of reactants and products in one same phase. An equilibrium constant expressed in terms of concentration in molar or moles per liter is called Kc. Given the reaction of stannous ion with steric ion forming stannic ion and serous ion, the Kc expression is follows. A heterogeneous equilibrium involves a mixture of reactants and products with more than one phase. Take note that substances in the solid or liquid phase are not included in the equilibrium constant expression since their concentrations or densities remain constant throughout the reaction. Shown on the right are some examples of heterogeneous equilibria and their respective equilibrium constants. The equilibrium constant expression depends on the given balanced chemical equation. Use the coefficients that are exactly indicated in the chemical equation. Consider the equilibrium reaction of hydrogen and fluorine gases to form hydrogen fluoride. Note that if the balanced chemical equation is divided by a number, say 2, the resulting equilibrium constant is the corresponding root of the first constant. In our example, it is the square root if the chemical equation is multiplied by 2. The resulting equilibrium constant is the first constant raised to the exponent 2. The equilibrium constant is a unitless quantity. However, the concentration substitute in the Kc expression is in moles per liter, while the partial pressure values in the Kp expression is in atmosphere. The reason for this is beyond the scope of this lesson. We will not indicate the units in future calculations of Kc and Kp values. When the chemical equation is reversed, the corresponding K of the resulting chemical equation is the reciprocal of the first K. consider the equilibrium reaction of nitrogen and hydrogen to form ammonia. If we reverse the reaction, the decomposition of ammonia, its equilibrium constant, is the reciprocal of the constant for the formation of ammonia. For a chemical reaction consisting of two or more steps, its K value is the product of the K values of all steps. Now consider the reaction of ozone O3 with atomic oxygen. This reaction can be split into two steps of reactions involving nitric oxide NO. Note that the equilibrium constant for the overall reaction is the product of constants of two steps. A reaction quotient QC is an expression similar to equilibrium constant Kc, except that initial concentrations instead of equilibrium concentrations are substituted in the expression. For distinction, this is 0 in the subscript on the symbol for concentration to denote that this is the initial concentration. The reaction quotient is used to predict the direction in which a reaction will proceed until equilibrium is attained. Details will be discussed in another lesson. To summarize, equilibrium constant is the ratio of concentrations of the products to the concentrations of the reactants.